Okay, here are the steps we're following for related rates. Just 7 of them, and 7 is really just a stupid joke. Draw a picture is always the first thing, and usually related rates are going to have to deal with like a lot of geometrical shapes. So let's take a look at a very common one. It's a cone, and calc books, calc teachers love to talk about conical tanks being filled, or inverted conical like tanks, or I don't know, just stupid tanks that are cones being filled. Okay, and the reason we like them is because they're a little bit harder than regular problems because they have one extra step, and we're going to go over that today. So here's what they're telling us here. We've got this cone. It's being filled with ice cream. Okay, so conical tank being filled with ice cream at this rate. So we know the rate it's being filled. And say ice cream is blue. So there's all this ice cream down in here, okay? There you go. And as time goes on, they're dumping in more and more ice cream. Okay. Now, we know that the conical tank has a diameter of 24 feet, which means the radius is 12 feet. Okay, and usually we care about the radius, not the diameter of the cone. And it tells us that it has a height from top to bottom of 18 feet. Okay, it tells us all that. And that's really all it tells us. How fast is the height of the ice cream in the tank changing when there are 4 pi cubic feet of ice cream in the tank? So now we got to figure out what all these numbers are, but essentially you should be able to do this, hopefully. Pick out what they're asking you to find, and that's usually the question. How fast is the height changing? So we want to know how fast the height's changing. That's going to be the rate of change of h with respect to time. So let's make up our columns here. We know. What do we know? Well, we got the picture over here. 18 and 12 aren't really changing, so I'm just going to leave them there like that. But we know that it's being filled at a rate of 10 cubic feet per minute. Now, you got to figure that's d something dt. It's a rate of change, so it's d something dt. And when you want to figure out what that is, if you don't know it right away, you can look at the units. If it's being filled, 3D things that are being filled are measured in volume. So this is a dV dt. It's 10 cubic feet per minute. So we'll write that, cubic feet per minute. And usually the units are a great giveaway. If you don't know what's changing or what's happening, if it's in cubic feet, that's usually going to be volume. If it's in square feet per minute or per whatever, that's usually area or surface area. And if it's just in feet, that's usually a length, like a distance or a radius or a height or something. Okay? So we got the conical tank, and we know that there are 4 pi cubic feet of ice cream in the tank. Well, that's information they're giving us. And again, it's cubic feet. That's a volume. So the volume in the tank is 4 pi feet cubed. So there's 4 pi feet cubed in the tank, and their volume is changing at 10 cubic feet per minute. Now, as this is going on, there are things changing here. So let's figure out what we want to know first off, I guess. What do we want to know? Well, how fast is the height changing? We want to know dh dt. That is what we're looking for. What is that dh dt? Okay, so that's what we want. We need some equations here. Well, the problem is we want height, or we want to know the rate of change of height, and we know volume and the rate of change of volume. So what we need is some equation that is going to link volume with height. So when we derive it, we're going to get dV dt and dh dt. And this is a fairly straightforward problem here. It's a cone. We're talking about the volume of a cone. So the volume of a cone is 1/3 pi r squared h. That's our equation. Now, the problem with this equation here is, and hopefully you're thinking ahead a little bit, when we derive this, we're going to get a dV dt, we're going to get a dr dt, and we're going to get a dh dt. So not only are we going to have volume, radius, and height, which are 3 variables already, we're also going to have their derivatives, dV dt, dr dt, dh dt. So total, we're going to have 6 different variables here, and we only know 2. We know the rate of change of volume, and we know volume. Also, since we know the volume here, 4 pi, we could plug in 4 pi for volume, like right here if we wanted to, and set that equal to this guy. But the problem over here is now we've got 2 other variables, and you cannot solve an equation with 2 variables and just one equation. We need some other equation, and this is why cones are always a little bit harder. Okay, you always got to do this one extra step. Not always, but most of the time. There is this relationship between, if you look at this triangle right here. All right, let's just draw it again out here. It doesn't look the same, but this was 12 and this was 18. And we're saying this is getting filled with some ice cream. So somewhere along the lines, we stop and we look, and there's our ice cream like that. Now, so you see the blue triangle here. There's a relationship between this little blue triangle here and the big red triangle. And we're going to need that in order to find out R or H. Here's how this works. Now, little r, is the volume of ice cream, is the radius of the ice cream in the tank, not 12. 12 feet's not changing. That's the volume of the entire tank. Okay, but we're not interested in the volume of the entire tank. We're interested in the volume of ice cream. We know there's 4 pi cubic feet of ice cream, and we know the volume of the ice cream is this. Okay, so we're not using the 12 and 18 in this formula. We don't know R and H because we want to know the R and H of the ice cream. So really, R is here and H is there. And this is an equation that always comes with cones here. These big red triangle and this little blue triangle always make up similar triangles. They're similar because this is a right angle for both of these guys, and they share an angle down here. So they have 2 of the same angles, which means this angle here must be the same as this angle here, and they have all 3 of the same angles. So remember, in geometry, same shape, different size, that's similar triangles. And similar triangles have to have the same ratio of their sides, meaning 12 divided by 18, I'll do this down here, 12 over 18 has got to be the same exact fraction as R over H. And that, even though it's not given to us explicitly as an equation, like volume is easy, you know the volume, 1/3 pi r squared H. You should always know that if there's a cone being filled, there will always be this equation between the radius and the height. Okay? The radius of the tank divided by the height of the tank will always equal the radius of what's in the tank divided by the height of what's in the tank. Again, 12 and 18 are not changing. That cone is not changing. What's changing is the ice cream in there, and the ice cream is also in the shape of a cone. So, here's what we want now. Since we have 2 equations here, we have an equation over here with R and H, we have an equation over here with R and H, we can do a substitution. So, for right now, let's just rewrite this over here. 12 over 18 is going to reduce to 2 over 3 equals R over H. Okay, so right now we have these 2 equations, and what do we know? Our unknowns, sorry. Well, we don't know R, we don't know dr dt. Okay, we also don't know H. We don't know dh dt, but since that's what we're looking for, I'm not going to put it in my unknown column. These are things that I might have to find in order to find dh dt. So using these equations and the information we've been given, we need to knock this problem out. So let's go to the next page here. And here's what we're looking at. We know the volume is 1/3 pi r squared h, and we know volume is 4 pi. So we would like to be able to solve this for either r or h, and essentially, since we're looking for dh dt, that's really the question. We don't really care about r or dr dt. That's not what they're asking us to find, so we don't need to worry about it. So really what we would like to do in this equation over here is just get rid of r completely. We don't care about r. And this equation right here is going to allow us to do that. Okay, this is our second equation. Since it has r and h in it, that's a relationship between them. We can solve for r. And we're going to get 2/3 h is r. Well, with this right here, now I can plug that into this equation and completely get rid of r. Now we know that 4 pi is equal to 1/3 pi, and r is just going to become 2/3 h squared times h. And this is going to simplify down to 4 pi is equal to 2/3 squared is 4/9, so times 1/3 is 4 over 27 pi h cubed. And this is the same thing for our volume equation. Volume is 4 over 27 pi h cubed. Okay, and these 2 equations only happen here. It's really the same equation. They only happen because the shape of the conical tank is not changing. But now you can see what we've done here is successfully gotten rid of r. So now, using this equation here, the 4 pi equals this, we can find out what h is. And also, if we derive this equation here, we're going to get a dv dt and a dh dt, which is what we're trying to find. Since we're trying to find dh dt, we need to get an equation with it. So, let's erase some of this here. Here's what they've given us. I wouldn't write it out again. But they gave us 4 pi was the volume in the tank. And we need to find h. H is important here because when we derive our equation, volume is 4 over 27 pi h cubed. When we derive this, we're going to get dv dt is equal to 4/9 pi h squared dh dt. We know dv dt is 10. The problem is we want to find dHdt and we don't know h yet. That's why we're looking for h. That's why we're using this equation to solve for h, because when we derive this equation, we have dv dt, h, and dHdt. We know dv dt, we want to find dHdt, but we don't know h. So that's like a block in our way. We got to find h. So we use the other equation we had, the equation before we derived it, because that had a volume and an h in it. And if we know one, we can find the other. So just doing some math here. There's a 4 times pi here. We divide by that, multiply by 27. And just doing a little bit of math, you end up with 27 is h cubed. So 3 must be h. And this is all in feet. Okay? Well, since h is 3, that allows us to take this equation over here and plug in 3. 4 nines pi times h squared, that's 3, times dHdt. And now the only thing we don't know is dHdt. So, doing a little bit of math, I'm going to slide it up into here. 3 squared is 9 times 4 ninths. Draw a line here. That's going to give us 10 is equal to 4 pi dHdt. And what that's going to do for us now, we can solve for dHdt. We're going to divide by 4 pi. 10 over 4 pi is dHdt. And we can simplify that, and we got to put units on there as well. But 10 over 4 pi will reduce to 5 over 2 pi. Okay, because the 2's cancel. And height is changing. Height is measured in feet, and our time has been measured in minutes. You remember this. Feet per minute, cubic feet per minute. Well, h is in feet. Everything else is changing in minutes, so this must be feet per minute. You could have stuck with your units the whole way through here. Like dv dt is in cubic feet per minute. H is going to be in feet per minute. I'm sorry, feet. And when you square it, that's going to be feet squared. And that's how we end up with feet per minute over here. But anyway, there's our answer. And again, just to go back through the steps here. First thing was, what do we know? We knew the volume was changing this fast. We knew the volume was this at a certain time. We want to know dHdt, so we had to come up with an equation that involved volume and h. Our goal was then to derive that equation to get dv dt and dHdt, plug in everything we know and solve it. The only problem was our original volume equation had an r in it, and we had to use this little guy to get rid of that r by substitution. And this, it won't always be 2 over 3, but it will always be some fraction can equal r over h, because when a cone's being filled, the cone inside is going to have a similar triangle with the total conical tank, the giant conical tank. And we used that to sub them out, and then it was just a matter of deriving something and solving for it. So we took this guy, derived it, we knew we needed h, so we used our original equation to solve for h. And there you go. That's a cone.